We're in chapter 2, limits and their properties, section 2.2. That's the topic we're going to discuss today, finding limits graphically and numerically. So in previous section, we briefly discussed how to, what does limit mean? And in this section, we're going to find the limits using the graphs or, using some numerical ways. So first, we're going to find the limits in an informal way, and eventually we're going to introduce formal way to find the limits, which is also called precise definition of limit. Okay, so these are the objective. Estimate a limit using a numerical or graphical approach. That's the first thing. Identify the ways that the limit fails to exist. Sometimes we cannot find limits. We need to find out, uh, we need to identify the ways. Prove the existence of a limit using the formal definition of limit. So there is a formal definition, which is also called precise definition. So we are going to discuss about that too. So let's start with one example to introduce limits. Let's say you have a function f of x, which is x cubed minus 1 over x minus 1. If you look at this function here, this function is undefined when x is equal to 1, because if you put x equal to 1 here on the denominator, that will be 0. And 0 on the denominator means it's undefined, because you cannot divide some non-zero number by 0. Okay, division by 0 is not something we can do. So now our goal is to find the limit, or if you try to plot the graph of this function here, you will be able to see the function is undefined at x equal to 1. So there are two ways we are going to discuss. One way is numerically how to find the value of this function when x is very, very close to 1. So for that, look at this table here. We can compute this table here when x is very, very close to 1. So you see here x equal to 0.75, 0.9, 0.99, 0.999. So you can see here, let's say this is a real number line, and there is a 1 here. So when you approach to 1 from the left side, or when you approach to 1 from the right side, what happens to this function? You can calculate those value by using this formula. Just put x equal 0.75 here and use a calculator, and that will give you 2.313. Put x equal 0.9 and so on, so on. So we are going towards 1 from the left side here. We're going towards 1 from the right side. So as you notice here, when x is approaching towards 1 from the left or right, the value of the function is approaching towards 3. You see that? When x is approaching towards 1 from left or from right, the function value is approaching towards 3, right? That's called limit of the function. That's called limit of the function. If you look at the graph here, this is the graph for this function. When x is very, very, very close to 1, the value of the function is very, very, very close to 3. So though the function is undefined at 1, that's the reason you have open circle here, but you can approximate the value of the function when x is very, very close to 1. And this is how we write, limit of the function when x approaches to 1. This is how we denote the limit. The limit of function f of x as x approaches 1 is 3. And that's our conclusion. Let's look at another example. There is a function f of x which gives you the value 1 when x is not equal to 2, and which is gives you the value 0 when x is equal to 2. So if you try to plot the graph of this function here in the coordinate system, it's always 1 except at 2. So 1 means it's a horizontal line. At 2, the value of the function is not 1. This is a horizontal line, y equal to 1. This is the function value 1, right? You see here? But at 2, the value of the function is 0. So the value of the function comes here. So that's the graph. So as you can see here, when x approaches to 2, this is the notation for approach. When x approaches to 2 from the left side or from the right side, the value of the function is approaching towards this one, from the left side and from the right side. That's 1. Though the value of the function itself is 0, but if you come from the left side or right side of the 2, the value of the function is 1, always 1. That's why the limit of the function, this function, is 1. That's what we say. Okay, so when x approaches to 2, the function value from the left and from the right, it approaches to 1. So the meaning is limit of the function f of x when x approaches to 2 is equal to 1. That's how we write. Okay. Sometimes, we are not able to find the limit because limit does not exist. For example, let's look at one example here. We have a function absolute value of x over x. So what happens to this function when x approaches to 0? So first of all, this is the definition of absolute value of x. Absolute value of anything is actually, the positive value of that number from 0. So absolute value of x is x itself if x is positive or 0, and absolute value of x is negative of x if x is negative. The meaning is, what is the absolute value of 5? Because it's a positive number, the value is 5. What is the absolute value of negative 5? Because it's a negative number, it's a negative of the number you see inside this absolute value sign. So eventually that will give you positive. So that's the meaning of, absolute value of x. Now we're trying to divide this absolute value of x by x. Then what do I get? If you divide, then that gives you 1 on the top and that gives you negative 1 on the bottom if x is greater or equal to 0 and if x is less than 0, right? So this is the function we're talking about. It's always 1 if x is positive, and if it's negative, it's negative 1. But what happens at 0? Because this function divide by 0 is undefined, so we cannot have value of this function when x is itself 0. So if you try to plot the graph of this function, you can see that it's always positive 1 to the right of 0, and it's always negative 1 to the left of 0. So what happens to the value of the function when x approaches to 0? At x equal to 0, it's undefined, but when x approaches to 0, from the left side, as you can see here, the value is positive 1. From the right side, as you can see here, the value is negative 1. So there are two different values. We don't have one consistent value. Whenever you approach to a number from left side and right side, if that number, if the value of the function approaches to the same number, that's called limit of the function. But if it approaches to two different numbers, then, that is the case where we say limit, does not exist. So let's talk about this thing very clearly here. Let's just draw an open interval at 0, and this delta is nothing, it's just a notation for a number. So no matter how close x gets to 0, there will be both positive and negative x values. So as you can see here, when x is very, very close to 0, no matter how close to 0, keep in mind, there will be both positive and negative x values that yield f of x equal 1 or f of x equal negative 1. Specifically, if delta, this is just a notation, is a positive number, then for x values satisfying, so if you pick any x from here or here, here or here, either it gives you positive value or it gives you negative value. If you pick from this interval, then it gives you negative 1. If you pick from this interval, it gives you positive 1. Because it's giving two different values, the limit of the function does not exist. Okay, so that's the case. That's the one case where the limit does not exist. There are some of the cases, common type of behavior associated with non-existence of limit. For example, the function f of x approaches a different number from the right side of C than it approaches from the left side. That's called limit does not exist. That's what happened here. The second is function increases or decreases without bound as x approaches C. function is just keep growing and growing, then you cannot find maybe you cannot find the limit when x approaches to c. The function oscillates between two fixed value as x approaches c. There are some of the problems you'll be able to see where you can see that the function oscillates between two values. In that case, we can say, hey, limit does not exist. So these are some common type of behavior. Now, it's time to define limit formally. We can also say the precise definition of limit.
So to talk about the limit of the function precisely, some of the things we're going to introduce here. So this is the definition. Let f of x be defined on an open interval about c, except possibly at c itself. We say that the limit of f of x as x approaches c is the number L, and write the limit of function f of x when x approaches to c is equal to L. And that is only possible if for every positive epsilon greater than 0, you can see that epsilon is greater than 0, there exists a corresponding number delta greater than 0, such that the absolute value of difference between f of x and L is less than epsilon, and whenever the absolute value of difference between x and c is less than delta. So here we have introduced two different notation, epsilon and delta. These are just a notation. Okay, make sure that these are just a notation, not just a name. Now we're going to try to understand this definition. Epsilon and delta are some positive number. So to understand this thing, I'm going to take one example here. So let's say there is a function f of x which is x plus 1. Okay, so when x approaches to 1, the function f of x approaches to 2. So because when x approaches to 1, either from the left side or right side gives you the function approach to 2, that means the 2 is the limit of the function. So I can write it down this as a limit of the function f of x when x approaches to 1 is equal to 2. So now we're trying to use this definition to understand the idea of the limit. This definition, the meaning of this limit is no matter what delta, meaning any value on x-axis around c in this case is 1, no matter what delta we pick on x-axis around 1 and create an interval, we should be able to create an interval on y-axis around 2 such that any image, the value of the function f of x from this interval should be inside this interval. I'm going to show you the picture, what I'm trying to say here. So here is the x-axis and here is the y-axis. There is a value c. Around c we're trying to create an open interval with distance delta to the right and to the left. This is an open interval. So if you pick any x from this interval, the image of that x using the function f of x should be inside this interval, because that's how we have defined the limit, and I'm going to use that definition here. The limit of the function f of x is L when x approaches to c. So when x approaches to c on the x-axis, either from the left side or right side, the value of the function approaches to L from up or from down. So that means if we create an open interval around c on the x-axis with distance delta could be any positive value, we should be able to find an open interval around L on the y-axis such that all the values coming from this open interval would be lie inside this open interval. If that is possible, if we can find out you know uh, delta for any epsilon, that means not just for one is epsilon. This epsilon could be anything. This epsilon could be 0.5, 0.05, 0.00005. More smaller value of epsilon, more challenging to find the value of delta. But if we can find epsilon which satisfy this situation, no matter what delta we pick on x-axis, then that is called, L is called the limit of the function f of x when x approaches to c. That is the precise definition of limit. Okay, so for the first time, this definition looks very, very not easy kind. It looks difficult, and in my experience, most of the student, 95-96% of the student, they do not feel comfortable using this notations alpha and delta, epsilon and delta. But just try to do a couple of problems, try to practice them, and then you will feel more comfortable. Okay, but take this limit definition as a game. If a function has a limit at some point, then for any epsilon you should be able to find the delta such that this situation holds. For any epsilon there should be delta such that this condition holds. But to understand this condition, you have to also understand the meaning of absolute value. So absolute value means, let's say absolute value of x is less than a, for example. What does it mean? It means x could be anything in between negative a to positive a. Okay, so if we are saying absolute value of f of x minus L, the difference between the function f of x and L is epsilon, this means the difference between f of x and L is in between negative epsilon to positive epsilon. Similarly, this absolute value of x minus c is less than delta, meaning this value of x minus c should be in between negative delta to positive delta. That's the reason if you go here, we are creating an open interval around c starting from c minus delta to c plus delta. That's coming from after solving the value of x here. If you just add c, you get x is going from c minus delta to c plus delta. And here you do the same thing. If you just add L, then L minus epsilon to L plus epsilon. That's the reason if you go to the next slide, you see that L is somewhere in between L minus epsilon. F of x is somewhere in between L minus epsilon to L plus epsilon. Okay, so let's try to do a couple of examples to understand this thing more. So first example is, you have given a graph, you have given a function f of x, you have given c, and then limit of this function and epsilon. Now by looking this graph, you need to find out the value of delta. So this graph is just difficult to see, so I'm just trying to zoom in. So look at here. So as you can see that L, which is limit, is 9, the function is 5x minus 6, and we can see that, and c is 3. So when x approaches to 3, the function, which is basically 5x minus 6, if we use our knowledge from previous section, we can find out the limit of this function very easily, because this is polynomial. When x approaches to 3, this is just 5 times 3 minus 6, which is 9. So we already know that the limit of this function is 9, but we want to use this precise definition. We want to understand this precise definition and try to figure out about this delta and epsilon here. So in this example, we have given that epsilon is 1. So if L is 9, then 9 minus 1 is 8, 9 plus 1 is 10. So the value of the function is going between from 8 to 10, not including 8 and 10. And from this graph, as you can see that around 3, this is possible if you go from 2.8 to 3.2. So if you take any values from 2.8 to 3.2, the image of those value will be inside this interval. So now just by looking this graph, if we have to find out the delta, then delta would be minimum of the distance of one of these number from 3. So whatever number gives you the minimum distance, that will be the delta. But in this case 2.8 is 0.2 distant less than 3, and 3.2 is also zero point 0.2 distant more than 3. So the value of delta you can take is zero point 0.2. Make sense? Because you always, if you have a graph like this and if you want to find out the delta, pick the minimum distance from the center to these boundary points. So in this case it's a 0 0.2. So in this for this problem, if you pick delta equal to 0 0.2 around 3, then anything from that interval will be inside this interval. Okay, sometimes we don't have graphs and we need to solve this problem of finding the delta using algebra. So these are some steps to help to find the value of delta. How to find algebraically a delta for a given function f, limit L, and then value c on x-axis and epsilon. The process of finding delta such that this holds, this relation holds, meaning whenever you pick anything from this interval on x-axis, the image of the function should be on this interval on y-axis. That holds. Now we need to find out the value of delta which holds, which gives us this relation. To do that, first of all we start with this relation, absolute value of f of x minus L is less than epsilon. We put the value of f of x, L and epsilon, everything, and now we solve, we try to simplify that relation such that we're going to get x minus c, absolute value of x minus c, okay, less than something, and that something will be our delta. Okay, so I'm going to show you one example here. Let's say you have function f of x, you have limit of that function, you have c, and you have epsilon. Now we're going to find out the value of delta. So in this case you can see that function is 2x plus 1. So we start with this and eventually we simplify that expression such that we should be able to find out x minus c, which is 9, less than some number. That number would be our delta. Okay, but we start with this thing. So plug the value of f of x, which is 2x plus 1, put the value of L, which is 19, less than epsilon, which is 0 0.18, and now try to simplify this. This is 2x minus 18 is less than 0 0.18. Now you can factor out 2. Remember, our goal is to go from this expression to x minus 9. So whatever you need to do to go from here to there, you have to do that operation. So in this case it's easy, because if you factor out just 2, if you factor out 2, you can write down x minus 9, and don't worry about this absolute sign for the 2. If you factor out 2, you can just keep it outside, 0 0.18. Now if you just divide both sides by 2, it will give you, if you just divide both sides by 2, it will give you 0 0.18 divided by 2 is 0 0.09, right? 0 0.09, that is after division. So that means if we pick delta equals 0 0.09, then this relation holds always. And it's not only for this delta, this relation holds anything less than this value. Okay, so if you pick delta equals 0 0.09, the meaning is around 9, 0 0.09, that means uh, so 9 minus 0 0.09, which is just subtract 0 0.09 from 9, which is 8.91 to 9.09. If you pick anything from this interval, then the value of that thing using this function f of x will be inside. Now you just have to find out L minus epsilon, which is 19 minus 0 0.8, which is 18 point, what is that, 82 to 19.18. So if you pick anything, any x from this interval, the value of the function should be inside this interval. So that's the meaning of limit of function. So that is only possible if you pick delta less than 0.09. If you pick something greater than 0.09, then you don't know, you are not so sure about that. But this delta or less than this value will always guarantee that the image you create using this delta on, the interval you create using this delta on x-axis, the image of that interval would be always inside this interval on y-axis. Okay. Okay, so the answer for this problem is delta equals 0.09. So let's see another example to make things just one more practice. We have given function f of x. When x approaches to 5, the limit of this function, we need to simplify this, and the limit of the function would be, as you can see, that what happens, what is the limit of this function when x approaches to 5? The limit of this function, x squared minus 25, by using previous section, we can say that, oh, just simplify this, x minus 5 times x plus 5 over x minus 5. We can cancel this, and if we find the limit, that would be 5 plus 5, which is 10. So that's L. So the limit of this function is 10. So now for this L, for this function, remember the function is x plus 5 after simplification, and for this epsilon we need to find out the delta. So we are going to repeat the same story whatever we did here. We start with the f of x, which is after simplification, it's x plus 5 minus L, which is 10, is less than epsilon, which is 0.09. So if you simplify this, it gives you x minus 5 is less than 0.09. Look at here, that's what we need. We need to find out absolute value of x minus 5 is less than some number, because c is 5, and we found that number. So we're going to say, okay, my delta is 0.09. So for this problem, delta is 0.09. So two things I would like to give you at the end. This definition means this is just another uh, way of visualizing your limit definition, limit thing. For any epsilon, we should be able to find some one delta such that this relation should hold uh, you know to get to be that L be a limit of the function f of x when x approaches to c, and we need to find out the delta for any epsilon. That's our main goal in this section. And for finding that, we have to just either we have a graph or we need to just follow these steps. And for that, we just start with f of x minus L, and we try to simplify that, and we try to get x minus c is less than some number, and that number would be our delta.